Good day girls and welcome back. We continue with our chapter 10, Space Missions. Satellite Launch Vehicles. Satellite launch vehicles are used to place the satellites in their specific orbits. The functioning of the satellite launch vehicle is based on the Newton's third law of motion. The launch vehicle uses specific type of fuel. The gas produced due to combustion of the fuel expands due to its high temperature and is expelled forcefully through the nozzles at the rear side of the launch vehicle. As a result of this, a thrust acts on the vehicle, which drives the vehicle high into the space. The structure of the launch vehicle is decided by the weight of the satellite and the type of satellite orbit. The fuel of the vehicle also depends on these factors. The fuel forms a major portion of the total weight of the launch vehicle. Thus, the vehicle has to carry a large weight of the fuel with it. To overcome this problem, launch vehicles with more than one stage are used. Due to this, the weight of the vehicle can be reduced step by step after its launching. For example, consider a launch vehicle having two stages. For launching the vehicle, the fuel and engine in the first stage are used. This imparts a specific velocity of the vehicle and takes it to a certain height. Once the fuel in this first stage is exhausted, the empty fuel tank and the engine are detached from the main body of the vehicle and fall either into a sea or on an unpopulated land. As the fuel in the first stage is exhausted, the fuel in the second stage is ignited. However, the vehicle now contains only one stage, that is the second stage. The weight now being reduced, the vehicle can move with higher speed. Almost all vehicles are made of either two or more stages. For example, the structure of the PSLV made by ISRO is shown here. It has an engine using solid fuel which provides the initial thrust. Then it has 4 stages and a place for the satellite. The launch vehicles are costly because they can be used only once. USA has therefore developed Space Shuttle which returns to the Earth except for the fuel tank and can be reused in multiple launches. Space missions away from Earth. As we have seen, artificial satellites are being used for making our life more and more enriched. We have also learned about how the telescopes aboard artificial satellites are used to gather information about various objects in the universe. Similarly, some space missions are used to gain further knowledge about the universe. In these missions, spacecrafts are sent to the nearby objects in the solar system to observe them more closely. New information has been obtained from such missions and it is helping us to understand the creation and evolution of our solar system. For such missions, the spacecrafts must escape the Earth's gravitational force to travel into the outer space. To achieve this, the initial velocity of the moving object must be greater than the escape velocity of the Earth. Escape velocity on a planet can be obtained using the formula V escape is equal to square root of 2gm upon r, where g is a gravitational constant, m is mass of the planet and r is radius of the planet. So for the Earth, the gravitational constant is 6.67 into 10 raised to minus 11 Newton meter square per kg square. Mass of Earth is 6 into 10 raised to 24 kg and radius of Earth is 6.4 into 10 raised to 6 meters. Using these values, we can find the escape velocity for Earth as 11.18 kilometer per second. So if a spacecraft is to escape Earth's gravitational force to travel to the outer space, it must have a minimum velocity of 11.2 km per seconds. Moon missions. Since the moon is the closest astronomical object to us, the first space missions to objects in the solar system were the missions to the moon. Such missions have so far been executed by USA, Soviet Union, European countries, China, Japan and India. The spacecrafts in the Luna series sent by Soviet Union reached near the moon. Luna 2, launched in 1959, was first such craft. After that, till 1975, 15 spacecrafts made chemical analysis of the moon and also measured its gravity, density and radiations. Last 4 crafts even landed on the moon and brought the samples of stones from the moon for analysis in the laboratories. All these missions were unmanned. America also executed moon missions from 1962 to 1972. The speciality of these missions was that some of these were manned missions. In July 1969, Neil Armstrong became the first human to step on the moon. In 2008, Indian Space Research Organization successfully launched Chandrayaan-1 and placed it in an orbit around the moon. It sent useful information to Earth for about a year. The most important discovery made during this mission was the presence of water on the moon's surface. India was the first country to discover this. Mars mission. Next to moon, the astronomical object nearest to the Earth is the Mars. Many nations sent spacecrafts to the Mars. Mars mission is difficult and almost half the missions were unsuccessful. However, ISRO's performance in this mission was remarkable. The spacecraft Mangalyaan, made by ISRO using minimum expenses, was launched in November 2013 and was placed into orbit around Mars in September 2014. It obtained very useful information about the surface of the Mars and the atmosphere around it. Mission to other planets. Many missions have been executed to study other planets also. In some of these missions, the spacecrafts orbited the planets, some landed on the planets, and some just passed near the planet and observed them. Additionally, spacecrafts have been sent to observe asteroids, comets, and they have successfully collected some dust and stones from the asteroids and brought them back on the Earth. We are getting very useful information from all these missions, clarifying our concepts about the origin and evolution of the solar system. India and space technology. India also has made remarkable progress in the science and technology of launch vehicles. Various types of launch vehicles have been developed to put satellites having weight up to 2500 kg into all types of orbits. PSLV and GSLV are two important launchers. The scientific and technological feats achieved by India in the field have a significant contribution to the national and social development. INSAT and GSAT satellite series is actively working in the field of telecommunication, television broadcasting, and meteorological services. Availability of television, telephone, and internet services all over the nation has been possible due to these satellites only. EduSat satellite in this series is used specially in the field of education. IRS satellite series is working for monitoring and management of natural resources and disaster management. To exactly locate position of any place on the Earth's surface in terms of its precise latitude and longitude, the IRNSS satellite series has been established. Space debris and its management. In addition to the artificial satellite, some other objects are also revolving around the Earth. It includes non-functional satellites, parts of the launcher detached during launching, and debris generated due to collision of satellite with other satellite or any other object in the space. According to one estimation made in 2016, there are about 2 crore pieces of length more than 1 centimeter revolving around the Earth. All this is nothing but the debris in space. This debris can be harmful to the artificial satellites. It can collide with satellites or spacecrafts and damage them, and it will be difficult to launch new spacecrafts. It is therefore very essential to manage the debris. Some studies and experiments are being done with this in view. Hope that soon we will have a solution for this problem and the future satellites and spacecrafts will not be in danger anymore. We now solve the word problems. First one. If mass of a planet is 8 times the mass of the Earth and its radius is twice the radius of the Earth, what will be the escape velocity for that planet? Okay, so we are given that the mass of the planet is 8 times the mass of the Earth. Radius of the planet is twice the radius of the Earth. Escape velocity for the Earth is 11.2 km per second. Okay, so you have to learn this value. Escape velocity for the Earth is 11.2 km per second. We have to find the escape velocity for the planet. So according to the formula, escape velocity is given by the formula square root of 2gm upon r. So for the planet it will be square root of 2gmp upon rp, where mp is the mass of the planet and rp is the radius of the planet. Okay, it is given that mass of the planet is 8 times the mass of the Earth. So in the place of mp we substitute 8me, and radius of the planet is twice the radius of the Earth. So in place of rp we substitute twice re. Okay, so now we just rearrange the terms. So we have 8 upon 2 into 2 gme upon re. Okay, so that is equal to square root of 8 upon 2 into square root of 2 gme upon re. So square root of 2 gme upon re is the escape velocity for the Earth, and root 8 upon 2 means root 4. So square root of 4 is 2 into the escape velocity of Earth is 11.2. So multiplying we get escape velocity for the planet is 22.4 km per seconds. Second one. How much time a satellite in an orbit at height 35,780 kilometers above Earth's surface would take if the mass of the Earth would have been 4 times its original mass? Okay, so given the radius of the Earth is 6,400 kilometers, that is 6.4 into 10 raised to 6 meters. Okay, kilometers are converted into meters. Mass of the Earth is 6 into 10 raised to 24 kg. Mass of the planet is given to be 4 times. Okay, so that is equal to 4 into 6 into 10 raised to 24 kg. Height of the satellite is 35,780 kilometers, and g, that is gravitational constant, is 6.67 into 10 raised to minus 11 Newton meter squared upon kg square. Okay, so we have to find the value of t. So the time taken by the satellite to complete one revolution around the Earth will be 2 pi into r plus h upon vc. Okay, now VC, that is critical velocity, is square root of g m dash upon r plus h. This is for the satellite. Okay, so T will be 2 pi into r plus h upon root of g m dash upon r plus h. Okay, so r plus h upon square root of 1 upon r plus h. When we solve this, we get r plus h raised to 3 by 2. Okay, so T will be 2 pi upon root g m dash into r plus h raised to 3 by 2. We substitute all the values given to us, and on solving we get the time to be approximately equal to 4.303 into 10 raised to 4 upon 3600 hours, that is approximately 11.95 hours, or it is 11 hours 57 minutes and 10 seconds, that is approximately equal to 12 hours. Third one, if the height of a satellite completing one revolution around the earth in t seconds is h1 meter, then what would be the height of a satellite taking 2 root 2 into t seconds for one revolution? Okay, so here we are given that the time is t seconds and height is h1. Okay, so we assume the height of the satellite completing the revolution in 2 root 2 into t seconds as h2. So T is equal to 2 pi r upon Vc, that is 2 pi into r plus h1 upon Vc is root of gm upon r plus h1. Okay, so T is equal to 2 pi into square root of r plus h1 cube upon gm. Okay, now r plus h1 upon square root of 1 upon r plus h1. This can be written as r plus h1 upon 1 upon r plus h1 raised to half, that is square root. Okay, that is r plus h1 upon 1 upon r plus h1 can be written as r plus h1 raised to minus half. Using indices, r plus h1 raised to 1 minus of minus half. It's of the form a raised to m upon a raised to n, that is a raised to m minus n. That is 1 minus of minus half will be 1 plus half, that is on solving we get 3 upon 2. Okay, so that is equal to r plus h1 raised to 3 upon 2. 3 upon 2 means cube of the square root. So it is square root of r plus h1 cube. Okay, and for the satellite taking 2 root 2 into t time, it will be 2 pi into square root of r plus h2 cube upon gm. Okay, so from these two equations we have t upon 2 root t is equal to square root of r plus h1 cube upon gm upon r plus h2 cube upon gm. So from this here t and t will get cancelled, gm and gm will get cancelled. So that is equal to 1 upon root 8, that is equal to square root of r plus h1 cube upon r plus h2 cube square root. Okay, so now taking the cube root on both the sides, we have cube root of 1 upon 8 will be 1 upon 2, and on the right hand side we will have r plus h2 upon r plus h1 upon r plus h2. Okay, so r plus h2 will be equal to twice r plus h1. Okay, so h2 will be, here we have 2r, so when this r goes on the other side it will get subtracted, so we will have only 1 r. Okay, so h2 is equal to r plus 2h1. Okay, so the height of the other satellite will be r plus 2h1. Okay, so here we come to the end of the chapter. Study all the question answers. Thank you.